So isometries are important enough in geometry that it turns out if we can understand all of the properties of the isometries of a geometric space, then we actually understand everything about the geometry of that space. All of the geometry is encoded in how isometries exist and how they interact with one another in the transformational viewpoint. So the first thing we did is to show that we can bring the tools of abstract algebra to bear on our study of isometries by showing that given a space, and we're thinking of the plane here, the set of isometries of the plane, together with the operation of composing two isometries together, forms a group. And so the definition of a group from abstract algebra tells us that we need to verify, first of all, that that set is closed under the operation of composition. So when I compose one isometry with another, that the result is still an isometry. And we agreed that that was the case merely because if I compose two things together which preserve distance, then that composition will also preserve distance. If it's preserved at each step, then it's preserved overall. Secondly, we had to show that the identity transformation exists and is an isometry inside of this set of isometries. And that's so only because the identity function I of x equals x, which doesn't move any point at all, trivially can be shown to preserve distances. So it's an isometry. We can also obtain that isometry as the product of any reflection with itself, according to theorem 7.2.1. Along that same line, that theorem 7.2.1 shows us that all of our isometries in our bag of tricks, our reflections, rotations, and translations, and glide reflections, and all of those, all have inverses. And we explicitly saw what the form of those inverses were in 7.2.1. And so the only remaining missing link to show that the set of isometries forms a group is to show that the operation of composition is an associative operation, that it satisfies the associative property. And that's the theorem that's over here on the left. So we would just need to show that if I have any collection of three isometries, that if I compose all three of those isometries together, it doesn't matter whether I do the first two of them first and the third one last, or whether I do the third one first and the pair of the first two of them last. That was a mouthful. Just the associative law. It doesn't matter where we place the parentheses. And the proof of that is nothing more than what we mathematicians call abstract nonsense, that T applied to the composition SR when it acts on a point X gives us nothing more than the result of first applying R, then applying S, then applying T to the point X, which is the same thing that we get if we first apply R and then we apply the composition TS. So composition of functions is always associative by this very same abstract nonsense argument. And so because isometries are nothing more than functions to begin with, they satisfy the associative law. And so we have everything that we need to conclude that the set of isometries of the plane forms a group under composition. And so we got some mileage out of the algebraic properties by using these to move forward and find out that isometries can't do a whole lot of crazy, ridiculous stuff. That as soon as we know what an isometry does to three different non-collinear points, we know everything about what that isometry does to every point in the plane. And so we see that in a combination of theorems that begins here. 825 is the guarantee that if these three non-collinear points are all left in place by an isometry, if they all don't move, then we're able to conclude that nothing at all moves in the whole plane. The T fixes the entire plane if it fixes only three non-collinear points. And the heart of the argument here was an argument by way of contradiction. So what I thought was interesting about this was the structure of the contradiction that we had. So we decompose the theorem to say if T is an isometry and it fixes 3 points and those 3 points are non-collinear, then T is the identity. Proving that directly would give us a lot to work with, but we would have to make a difficult conclusion that T fixes every point. So we went after it indirectly instead. Assuming that T does not in fact fix every point, so assuming that T moves something, we'd like to show that one of these three elements in the conjunction that formed our hypothesis is not true. So either we need to show that T is not an isometry, or that one of these 3 points is not fixed, one or more, or that our 3 points are in fact not non-collinear. And that ends up being the line of argument that works. So assuming that T is not the identity, that means that it must move some point, which we'll call P, to a different point, P prime. Because those points are different, and because distance functions are non-degenerate, that's a fancy way of saying two different points having non-zero distance in between them, that means that assuming that our transformation is an isometry, the distance between A and P, for example, is the same as the distance between T of A and T of P. Again, because T is an isometry. But because T fixes A, T of A is the same as A. And so what that sets up for us is the observation that knowing everything that we know about the situation, the distance between A and P is the same as the distance between A and P prime. And so we have a picture that looks like this. A is here, P prime is there, and my isometry is moving P over to P prime, but it's leaving A in place. So that's what T is doing. But because A is the same distance away from P as it is from P prime, what we know about perpendicular bisectors tells us that that means that A lies on the perpendicular bisector of PP prime, whatever we want to call that. It's called L. Right? But then we make that very same argument for the point B, because B is fixed also. We can run that same argument to say that B must lie on the perpendicular bisector between P and P prime, and running the same argument for C, C also must lie on the perpendicular bisector between P and P prime. But those 3 points cannot all lie on the same perpendicular bisector without being collinear. So what we've really done is we've really contradicted by concluding that A, B, and C are collinear. But that's a contradiction of the assumption that A, B, and C were non-collinear in the first place. So it's not possible for an isometry to fix 3 points that are non-collinear, fix a triangle, unless it fixes the entire plane. It can't fix the vertices of a triangle without leaving the entire plane in place. And the rest of our arguments are all just ways of pushing that ball forward a little bit more. 828 tells us that 2 different isometries cannot do the same thing to the vertices of the triangle unless they are not in fact different. Right? So if 2 isometries do the same thing to the vertices of a triangle, they are the same isometry everywhere. And this is where the algebraic properties come in handy. Right? So if I have 2 isometries T and S that do the same thing to the vertices of a given triangle, ABC. So if S and T both send A to the same spot, both send B to the same spot, both send T to the same spot, then all we have to do to each of these equations is take the inverse of T, which again, because the isometries form a group, we know that that inverse exists and it is an isometry. So I'm just going to apply that inverse to all sides of all 3 of these equations. And in doing so, we arrive at this system that says that T inverse S as a transformation, as an isometry, fixes A, B, and C. But 825 tells us that any transformation which fixes 3 non-collinear points must be the identity. So T inverse S must be the identity, which implies that S and T are not only the same isometry on these 3 points, they're the same isometry absolutely everywhere. So as soon as we know what is happening to the vertices of a triangle under an isometry, we now know everything about what that isometry does to the entire plane. And the last step in that process is that we use that to show that any isometry of the plane can be written as the product, the composition, of at most 3 reflections across different lines. The non-obvious part of the argument here was right here. We saw a procedure, actually at the beginning of our hour today, when we talked about the iron grate example. In our iron grate example, we came up with an algorithm, really, for how to carry one triangle onto a congruent copy of itself using a sequence of reflections. All we did was take each one of the vertices in turn and say, to move this vertex to where I want it, I should just reflect across the perpendicular bisector that connects where I'm at and where I want to go. Right? And because we have 3 vertices in this triangle, we can move all 3 of those vertices where we want them using no more than 3 reflections in turn. So we have this algorithm from our iron grate example that shows us how we can move one triangle onto another copy of itself, congruent copy of itself, using at most 3 reflections. So in principle, we probably could break this proof out to say, well, let's suppose that it only took us 1 reflection. Then how do we prove this? Let's suppose that it only took us 2. But all those proofs would look identical to one another. And so we only do it in the one case here, and the other 2 cases are completely analogous. If it did take us 3 reflections because none of our points were being fixed, then we can conclude that those 3 reflections do the same thing to the 3 vertices of our triangle that T was doing to the three vertices of our triangle. But according to the theorem that we just proved, if two isometries do the same thing to the three vertices of a triangle, then those isometries must be the same absolutely everywhere. And so not only is the effect of T the same as the effect of these three reflections on our triangle, on our iron grate, the effect of T is the same as the effect of these three reflections for all points on the plane. And so the isometry T can be decomposed into at most a product of three reflections.